While the square root method and factoring are efficient methods for solving trigonometric equations in quadratic form, they're not always 100% reliable. However, the quadratic formula can be used to solve any trigonometric equation in quadratic form. For the quadratic form equation, AU squared plus BU plus C equals 0, the solutions are given by U equal to, and you'll recognize your familiar quadratic formula over here on the right side. Do notice that U is going to be the variable part of your middle term. Let's apply this to example 6, where we'll solve a trigonometric equation in quadratic form in degrees between 0 and 360 degrees. Where necessary, we'll round approximate answers to the nearest tenth. Example A is sine squared of theta minus 3 sine theta minus 1 equals 0. If we played for this with any amount of time, we would discover it does not factor. Therefore, we can apply the quadratic formula. Notice that the coefficient of our quadratic term, A, is 1. The coefficient of our middle term, B, is -3, and the constant term, C, is -1. Now, again, pay attention to the left side. U, in this case, is the variable part of our middle term. So the left side of our quadratic formula will be important in this case. So instead of saying x equals -b plus or minus so on and so forth, we're going to say sine of theta equals -b, that's -3, plus or minus the square root of b squared, that's in parentheses -3 squared, minus 4 times a, which is 1, and c, which is -1, all divided by 2 times a, or 2 times 1. So simplifying, we have 3 plus or minus. Underneath the radical, we have -3 squared, which is 9, plus 4. 9 plus 4 is 13 divided by 2. And this cannot be simplified any further. We have two distinct answers here, and I'm going to go ahead and split them up. We have 3 minus the square root of 13 over 2, and 3 plus the square root of 13 over 2. Those are not the solutions to the equation. Those are the values of our left side over here, sine of theta. In order to solve the equation, we're going to need to apply the inverse sign to both of those expressions. So theta will be inverse sine of our first value, 3 minus the square root of 13 over 2, and inverse sine of 3 plus the square root of 13 over 2. You can certainly express that in a condensed form as inverse sine of 3 plus or minus square root of 13 over 2, as long as you remember to evaluate both of those individually with your calculator. Now, in degree mode, I'm going to evaluate inverse sine of the first expression. The numerator must be contained in a set of parentheses in order to force the correct order of operations here. So we have inverse sine of 3 minus the square root of 13 in the numerator divided by 2. And we end up with -17.6 degrees. Now, what in the world are we doing with a negative answer? Well, it turns out that 3 minus the square root of 13 over 2 is a negative number. So I'm going to make a note that's a negative number in there. Sine is negative in quadrants 3 and 4. But recall, the range of inverse sine is from -90 degrees to 90 degrees. So the calculator is giving us -17.6 degrees, which is in the range of inverse sine, but we can certainly adjust that to a positive angle. -17.6 degrees is not in the interval between 0 and 360 degrees, but I can simply rotate backwards from 360 degrees and find a coterminal angle. So 342.4 degrees is positive. It's coterminal with the solution, and it's in our given interval. Now, because this value in parentheses is negative, we know that sine is also negative over here in quadrant 3, so I need to find a solution over here in quadrant 3. Understanding that our reference angle is 17.6 degrees, I'm going to start with 180, and I'm going to rotate an additional 17.6 degrees to land at 197.6 degrees. So the two solutions that come out of our first factor are listed there in purple. Now, we're halfway there because notice we have another inverse sine to evaluate with the calculator. We can see that this is going to be a positive value in our sine. So inverse sine of, in parentheses, 3 plus the square root of 13 over 2 yields a first solution. Whoops. This one's interesting. It's giving me a domain error. So let's check this out. If we do 3 plus the square root of 13 divided by 2, notice it is bigger than 1. So 3 plus the square root of 13 over 2 is not even in the domain of inverse sine. So that means we're not going to get any solutions coming out of that second value. That's kind of good news. That means we're done. Our only two solutions are 197.6 degrees and 342.4 degrees. Now, we could certainly check each of those solutions by substitution, and of course it'll be approximate since we approximated the solutions. But to be sure that we've got all the solutions in one rotation around the unit circle, I prefer to check by looking at the x-intercepts on the graph. So I'm going to go to y equals. I'm going to type in the original function. Remember, it must be equal to 0. We're in degree mode. I'm going to set my window from 0 to 360. A scale of 30 degrees will be appropriate here. So I'm just observing we do, in fact, have two x-intercepts. And once again, each of our values could be substituted into the original equation for theta to verify the balance. Let's try example B. Tangent squared of theta minus 2 tangent of theta minus 1 equals 0. If we tried to factor this one, we would be unsuccessful. However, we can solve this with the quadratic formula, recognizing that the left side yields the variable part of our middle term. For this equation, the leading coefficient A is 1. B we can identify to be -2, and C is -1. So in the quadratic formula, we have negative B, that's -2, plus or minus the square root of B squared, put that B in parentheses, minus 4 times A, which is 1, times C, which is -1, all divided by 2 times A, which is 1. Simplifying, we obtain 2 plus or minus, now look at the radicand. We have -2 squared, that gives us 4, minus 4 times -1, that's going to be plus 4. 4 plus 4 is 8. The square root of 8 can be simplified to 2 square root of 2. Because both of our terms are divisible by 2, we can reduce this to 1 plus or minus the square root of 2. Don't forget we have a tangent of theta over here on the left side, so we haven't yet found our solutions until we apply inverse tangent to both sides. So we're going to evaluate inverse tangent of 1 plus or minus square root of 2. Now, unlike our issue with the inverse sine over here, the domain of inverse tangent is anything from -infinity to infinity, so we will not find a domain error regardless of the size of those arguments. Also, I've expressed it in the condensed form with the plus or minus, but we'll have to do one at a time with our calculator. So in degree mode, we'll evaluate inverse tangent of 1 minus the square root of 2. And our first value is -22.5. Like inverse sine, let's make a note that the range of inverse tangent is -90 degrees to 90 degrees. Inverse tangent for the first root yielded a negative value. That puts us down in quadrant 4. But it's not in the original interval between 0 and 360 degrees. So we're going to need to make an adjustment. As we did on the previous example, we can start at 360 and rotate 22.5 degrees in the negative direction, and we'll find a positive coterminal angle less than 360 degrees. So we could say this is also known as 337.5 degrees. Recall that tangent is also going to be negative in quadrant 2. 1 minus the square root of 2 is a negative number. You can also remember that solutions regarding tangent are always 180 degrees apart. So using 22.5 as the reference angle, if I take 180 minus 22.5, that gives me the solution in quadrant 2, which is 157.5 degrees. Those are the two solutions that take care of the minus part of the plus or minus. Let's go back and calculate the roots that correspond to the plus part of the plus or minus. That is, we need to evaluate inverse tangent of 1 plus the square root of 2. This is a positive number, so we can expect a quadrant 1 angle, and we come up with 67.5 degrees. So that solution is over here in quadrant 1. Tangent's also positive in quadrant 3, and I can evaluate this angle, noticing that my reference angle is 67.5. So I'm going to take 180 plus 67.5. Remember, solutions for tangent equations are always 180 degrees or pi radians apart. So we get 247.5 degrees. Listing all of our solutions in order from smallest to largest, we have 67.5 degrees, 157.5 degrees, 247.5 degrees, and 337.5 degrees. Let's take a quick peek at the graph and make sure that we have found all of the solutions in one rotation around the unit circle. So I'm going to graph the left side of the original equation, observing that it is equal to 0. That means I'll be able to manipulate solutions as x-intercepts. We came up with 4 solutions, and notice we do have 4 x-intercepts. So we are good to go. Quadratic formula is a reliable method for solving trigonometric equations in quadratic form, but as you saw from these 2 examples, it often requires approximation, which is a little bit more tedious than finding an exact solution.